All right, ladies and gentlemen, what we're going to look at today is we're going to look at the graphs of exponential functions. Now, we explored in the last class that I saw you some of the applications and how to write the models for growth and decay. So what we're going to look at now, though, are just what the graphs would end up looking like. So in your notes, you'll see this on one of the pages. And it asked us to sketch the graphs of g of x, which was 2 to the x, and h of x, which was 1/2 to the x, on the same coordinate plane. Now, in order for me to do that, I went ahead and I created a table for each one. Now, g of x I graphed in teal, and h of x I graphed in red. Now, they have a lot of similarities. But what you guys hopefully will see is what is different about them is what they are approaching as x is going to negative infinity or to positive infinity. So if we take a look at g of x, as x is approaching positive infinity here, as my x's are getting greater, g of x is getting greater. And that's going towards infinity as well. Now, as x is approaching negative infinity, so as we look at this teal graph, as I go further and further to the left towards negative infinity, these numbers are going to get increasingly smaller, but they're never going to quite reach 0. So they're going to get super close to it, but never quite get there. So, hopefully you've guessed that exponential functions have something in common with the rational functions. They have asymptotes. So in this situation, we're looking at an asymptote at y equals 0. And so as x is approaching negative infinity, g of x is approaching that horizontal asymptote, which is 0 in this case. Now, this ends up switching when we start taking a look at h of x. So in h of x, it's as x approaches infinity, h of x is going towards 0. And as x is approaching negative infinity, that's when it's taking off and going towards infinity. So each one of these is an example of an exponential growth or decay. Well, hopefully you know, as x is approaching infinity, as it's going towards infinity and it's growing, well, this is your exponential growth. And this one is going to be your decay. Now, the way that we determine if a function is representing exponential growth or decay is by taking a look at the base of our exponent. So here, the base of my exponent is b. If b is greater than 1, then you're going to be looking at a situation in which you have growth. If b is between 0 and 1, then we have decay. Now, when we go to sketch the graphs of these, we're going to sketch them a lot like we did with our parent functions. Now, in each of these three problems that we have here, f of x equals 5 to the x is what we would consider the parent function for this one. And so when we go to look at these for our parent functions, it's just the base of your exponent raised to x. So we take away anything that's getting multiplied, added, or subtracted. So we're going to sketch the graph of our parent function. Now, I will typically use these 3 points. So I have -1, 0, and 1 as my x's. So I have 0, 1, 1, 5, and then when I raise it to the negative 1, it's the reciprocal of that. So then I have to the 1/5. Now, my horizontal asymptote for this will be 0, y equals 0. And so when I go to plot these points, that's my graph. But transformations of these parent functions are going to take place. So in this problem, if I got rid of the +3 and the -4, all I'm left with is this parent function. So it's important to be able to create the table for the parent function and know how to find it. So what this is now telling me, though, is that inside of my rule, or inside of my exponent, this is our horizontal shift. And hopefully you guys remember that that's always the opposite. Outside of our rule of what's getting added or subtracted, that's representing our vertical shift. And then our A value is going to be our vertical stretch or compression, and possibly a reflection about the x-axis. So when I take a look at this example here, this is telling me that I'm going to go left 3. And then this is telling me I'm going to go down 4. So I'm going to take this function and it's going to go left 3 and down 4. Well, if I took this graph and moved it down 4, what that means now is that my horizontal asymptote, maha, is at y equals -4. So your vertical shift will always be associated with that horizontal asymptote. But this also tells me that I'm going to shift left 3. So what I like to do is I like to start at 0, 0. I'll still graph my horizontal asymptote first, but it tells me I'm going left 3 and down 4. So I put an X there. And I use that X to represent where my new origin is. So now I pretend like that's 0, 0, and I graph the points from my parent function. So if I'm pretending that this is 0, 0, I have the point 0, 1, then I have the point 1, 5, and then -1, 1/5. And so that's my function. Now, the other problem, though, that you see to the right of it, this one's a little different. The only difference in this one now is that we have a vertical compression. Oh, I lied, and I'm not redoing the video. It's not a vertical compression, it is a vertical stretch. So nothing else is taking place. So it's going to have a horizontal asymptote at 0. My real origin is the origin. And so what we're going to end up doing is, if we know that our table is -1, 0, 1 with the corresponding y values, is whatever that A value is you guys are always going to multiply your y coordinates by it, because it's going to pull them up. It's stretching them. So my y coordinates become 10, 2, and 2/5. Now plot as many points as you can. Sometimes you'll fit more than others. So now I have 0, 2, 2/5, which I won't probably see much of a difference on, and then I would have 1, 10. So I'm going to pretend it's up there for a sec. And I missed my points. Okay, so that's how we handle that vertical stretch or compression. So in the next video, I'm going to do one more with you guys where you're looking at an exponential decay.